hello. Hmm. Hmm? Okay. Hello, 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 hello. Hey. Hey, there you are.
Oh, just
Okay.
a second. I think I need to adjust my audio settings.
Yeah, I'm worried about my audio as well. Do you hear me well?
Yes, now I do.
Is my audio good?
Yeah. Can you hear me?
Yes, I can hear you. Can you
Great.
record your end as well so that nothing is lost in case?
Sure.
Yeah.
Oh, I guess I need your permission to record.
Please have it. Oh, you don't have my permission?
Yeah, I don't.
Okay, how do you get that?
I'm not sure. Says
Okay.
please request recording permission from the meeting host.
Hello, hello.
Oh, can you no longer hear me?
Yeah, I hear you, but you hear me? Do you hear a knocking sound? Do you hear a knocking sound now?
Yeah.
So, and not now.
I can hear it now too.
Okay, is it louder now?
Yes.
Okay, so then it's from this one. It's just, I'm not sure. It sent me some mixed messages about where it recorded. Okay, hopefully this works. And if not, I'll tell you. I've used Zoom twice before, but it's never feels great. Hello, Anna. Thank you so much for taking time to talk to me. Let's try to just start it. This is Øystein Runde, and I'm a Norwegian cartoonist, and this is my podcast, Wunderdog, which is where I just talk to people who I find interesting, currently about space. And
Great.
You're both working with space, and you found something very interesting, Anna Bonaca. You found someone has been shooting bullet holes in our galaxy, more or less. Someone.
Yes, looks like it.
Okay. Could you tell us the short version first and then give us who you are afterwards?
Of course. Yes, so as you say, I'm an astronomer and I study motions of stars in our galaxy. And there are some very interesting groups of stars that used to be a part of a same system before, part of a star cluster that maybe you've seen, like if you had a chance to look through a telescope. Maybe they're pretty cool. They're like groups of millions of stars that live together in a ball. And as they orbit around the Milky Way, slowly they start losing stars. And so they're kind of create this breadcrumb trail that's kind of very thin and long throughout the galaxy. And this is interesting because it sort of serves as our gravitational test of what is in there. And what I found is that one such trail of stars has some holes in it. And after I did some numerical simulations, I saw that I can get one such hole to appear if something very massive kind of went past very close to this trail of stars. So this is how that discovery got portrayed in the news as bullet holes in the galaxy.
Is it wrong? Do you feel it's a very tabloid way to say it?
Oh, no, I think it actually captures pretty well this picture of what we think is going on. It's just that I don't know, maybe that's the usual in science. It's not 100%. Now some people have started saying, well, there may be different ways to form those bullet holes. It might not be that something actually went passed by, but this is in the context of what I was doing. I was really kind of shooting up stuff at this stream of stars. So actually it does look like pretty much as a bullet hole in that sense.
In the context of what you was doing, what do you mean with that? I mean that the tabloids, that the headline version was pretty correct. That's what you mean?
Yes, that's what I mean. Yeah, that's. I guess I wanted to kind of make a distinction of what we saw in the sky and my interpretation of what happened. So I tested this particular idea that if you shoot something, you can get this hole as we observed. But of course, this is sort of our in crime scene investigation, right? We saw
Yes.
something in the sky, and we're like, okay, how can we form it? And then I ran some numerical experiments in my computer to see if I can reproduce what we see in the sky. But maybe there are some other ways to get at the same thing.
Are there any other ways that we can imagine right now?
Um, there's some ways sort of to inherit some of those gaps from the initial from sort of the way stars are losing stars
Mhm.
are leaving this cluster of stars. You can imagine if they are not all leaving at the same time, if that kind of varies, that might produce kind of a gap kind of along the way. So that would be one way of doing it.
But
I will
is
say,
yeah, but is
oh,
that sounds very, very far-fetched.
I mean, I think our model is the kind of reproduces most of the things in detail. So I think it's a pretty good model, but it's also I guess a very big claim if we actually think we are finding this bullet holes. So yeah, I think now we need to be very thorough in ruling out or checking if anything else could have done the same thing. So so
Sure.
yeah, it's yeah.
You so there's three theories about what these holes could be made of, right? Three things that could make these holes.
At least three things,
At
yes.
least three. Okay. Could you
Yes.
give me the best, the most credible theories of what are the things? What are the bullets?
Mhm. That's a yeah, that's a great idea. That's a great question, and I guess I can tell you what would I be most excited about if the bullets were it. So the reason why I went to I study these objects, these sort of stellar streams, is that I want to see if there are any small clumps of dark matter floating around. So that would be what I think would be very exciting if we could see that. That it was actually a clump of dark matter that was the bullet. However, there may be other kind of more mundane objects. Some, for example, different a group of stars that I talked about at the beginning that kind of form this
So
long trail. It could be that there another such cluster of stars came very close and that kind of was the bullet basically.
so a start. So to go back to this dark matter stuff is very exciting, but maybe we should go to
Mm-hmm.
the star clusters. So
Mm-hmm.
all the stars in all galaxy are organized in clusters.
Mm. Well, we think at the beginning that they are, so that no really star is kind of born alone, that all stars are born in clusters. But as time goes on, they're sort of started drifting apart. So most stars now in the galaxy are kind of on their own. It just some few are still in these massive clusters, and it really takes kind of the most massive groups of stars to survive for a long time as a cluster, because they
As a
slowly
cluster.
all start kind of yeah just drifting apart on their own. Yeah.
Why do they drift apart?
Oh, it's yeah, that's a very great question. I guess in in kind of the simplest terms, it's that they are not well, they have some of their gravitational pull that kind of shields them from the Milky Way's tidal forces, and for most of them, they're just not massive enough. So they're kind of, I guess, in the physics terms, we would say that they are not really bound very strongly to us. It would be like,
Together
uh,
as a cluster.
yeah, together as a cluster. Yeah.
Uh,
So they're kind of just kind of loosely bound to begin with, and then kind of because of the Milky Way's gravitational forces, they kind of just stuck at those stars and first kind of take the ones that are kind of in the outermost parts, and then kind of slowly kind of get to all of the stars basically in that cluster.
And then they join the Milky Way, which is sort of the ultimate cluster. Is the Milky Way considered a star cluster, or?
Oh yeah, the Milky Way is considered a galaxy. So yeah, so that's, yeah, I guess the distinction is that the Milky Way as a galaxy has a very massive dark matter halo surrounding it, and so that's kind of the difference between galaxies and star clusters.
Oh really? A dark matter halo?
Yeah.
How do we know that?
Oh, that's another interesting question. So it actually dates back to I guess 70s. Okay, I will hope I'm saying this correctly. Yeah, it's very interesting. So back in the 70s, people were measuring kind of how fast the stars are moving.
Yeah.
And they found that many stars in galaxies, in the Milky Way and other nearby galaxies, are moving very fast. And it can kind of, that sort of, if you shoot a rocket out of the Earth fast enough, it can leave the Earth. And so what scientists found is that the speeds at which those stars are moving are very high. And if there is nothing else holding the galaxy together, they will all sort of kind of fly away. But we see the galaxy, like the stars in the Milky Way galaxy, have been together for billions of years. So so that was sort of indirect evidence that there must be something else to hold all of these stars together. And because we don't see it, we call it the dark matter.
So the Milky Way is not heavier. I know heavier is the wrong word, but heavier is the easiest word, isn't it? The more massive. The Milky Way is much more massive than it should be when we look at the stars and count the number of stars and see how big they are. Yes. They are moving too fast. They should just whoosh, like when you have a blend fruit with an open blender and it just goes everywhere. Yeah. So that's what. But there's an invisible lid on top of the blender, and this is what we call dark matter. And this is also your potential solution to the bullets, what the bullets are. Your favorite solution to what the bullets are.
Yeah, I mean, yes, I would be most excited if that ended up being the case. And yeah, so it's really because we know this there must be some dark matter, but we don't know what it is. And one of the theories is that one of the very popular theories is that in this big halo of dark matter, you have small clumps of dark matter. And so those are the ones that I'm testing for, because we know there must be like some dark matter, but we don't know how exactly it's distributed. If it's all kind of in a smooth sea of dark matter, or if there are like this small kind of clumps that are kind of roaming around and maybe creating those bullet holes
in the galaxy. But if lumps of dark matter were moving around, we would probably see effects, a lot of different effects.
Yes, one would hope so, but they are very low mass, so then it's hard to see the effects. So, but yeah, you're right. Like these star streams and like gaps, bullet holes in star streams are not the only thing, but it looks like it's a really good test of them, because we rarely know where exactly the stars are supposed to be moving, like in the galaxy. Because those clumps of dark matter would kind of tug on basically all of the stars that they come close to. But if you just take any random star in the Milky Way, you don't know kind of how it was supposed to be moving. But in the stream, you kind of know that all of the stars are supposed to be kind of going in the same direction. And then if you see kind of a gap, they're like, oh, something must have happened here. So that's kind of the reasoning why we use those streams as a gravitational test.
Because these streams of star clusters are like if when you let the plug out of the bottom of a sink, and all the water is swirling out. Is it like that? Well, if the middle of the Milky Way, the black hole Sagittarius A, is the middle of the sink, then the stream is like the pattern that left behind in the sink. If it's a little bit dirty.
I think that would work. Yeah, it's kind of if you have, I can imagine if you maybe have some like a little bit of a dirty water or like a drop of a different color, that it would kind of get elongated in a very thin stream that it kind of circles around. I think that's pretty good. In a way, So I think that's a good way to think about it. This is sort of if you were able to kind of illuminate an orbit in the galaxy. Yes.
Right. One galaxy,
orbit.
One star cluster's.
Yes.
One star cluster's orbit.
Like to a very good approximation, all of the stars are on the same orbit, and for a star like the sun, we don't know. We can just measure its current position. We don't know what its past orbit was exactly.
We don't know.
But for those stars, we kind of do know, because we expect they all were on the same orbit. And I think, as what you were saying, is that in the sync analogy, that you would be kind of seeing what the orbit is in that system, because it all kind of goes down the drain. And in the Milky Way, everything orbits kind of around the center.
Yeah, except the mistake with my sync analogy is that these star clusters wouldn't be moving into the black hole.
Yes,
they would just the circle would be the same all the time, because there's no loss of energy through friction or anything like it would be in our world, in our atmosphere. That
would be that's a difference, but I think still it's a good analogy.
So, and this is like someone has put their finger through all of the dirt in my dirty kitchen sink and just left a finger.
And you're like, well, something happened there. It might have been someone's finger. It might be, something else.
But just to keep, actually, the whole Milky Way is kind of flat as well. It's all of the things are in one plane, right?
Yeah, that's true for the stars. So most of the stars in the Milky Way are in this flat disk, but the dark matter halo that surrounds it, it's almost spherical.
You say that, but we don't know where it is. So how can you say that?
That's a very fair question. There are a few stars and those star clusters that are not in the galactic plane, or kind of in the main plane of the Milky Way. They're kind of roaming outside of it. And actually, very recently, astronomers have been able to measure how they move, and found that they actually need something like a spherical halo of dark matter.
Cool.
So,
wow. But I just read recently that we found a galaxy that where the math worked out immediately with no dark matter. A galaxy that has enough stars to make sense without the dark matter theory. Do you know anything about that?
I've heard a little bit about it, and it was a big puzzle, because that was kind of a central picture of kind of how galaxies form, that anyway has been established in the past, I guess, 50 years. It's been building, but now it's fairly well established that something like 85% in the universe is dark matter, and that those it's a lot.
85% of the mass.
Of the mass, yes, of the universe is in dark matter. And so that most galaxies, or really in this kind of simplest term, all galaxies should have a halo of dark matter. So it was a big puzzle to discover one that didn't really have that much dark matter, or or any. And so yeah, I think the jury is still out. I'm not sure that it has been resolved exactly how it came to be. There were some suggestions that maybe this galaxy lost some of its dark matter, because other than it's kind of, yeah, galaxies are very hierarchical. So the Milky Way is it's kind of a, you know, let's say a medium galaxy, but it has smaller galaxies that are orbiting inside it. And those small galaxies. Yes.
What? What? Are there galaxies inside the Milky Way?
Yeah, they're very tiny though.
Can I have one?
No, they're kind of far away though. But yeah, we actually think that that's kind of how most galaxies form. That that smaller galaxies collide with the bigger galaxies and sort of deposit some of the stars, deposit some of the gas that forms new stars. And so the Milky Way, kind of through its history, has been collecting all of these stars from small galaxies, and or kind of first small galaxies and then incorporating them together. And so some of them are still exist as distinct small galaxies, or we call them satellites, and they look very similar to the star clusters, except that they have their own kind of smaller dark matter halo that is kind of and they're orbiting around the Milky Way. And there are like many of them. Yeah, okay. Around the Milky Way. Yeah, so there are something like 60 of them known.
60?
Yeah.
I thought you said inside the Milky Way.
Oh, I meant as kind of inside the Milky Way as, yeah, I was referring to Milky Way as all of the stars and also all of the dark matter. So we kind of think of that as a unit of the Milky Way.
You mean inside the Milky Way's dark matter halo?
Yes.
The dark matter bubble that keeps everything. Mm-hmm. And so they are stuck in the gravity field of the dark matter halo, but they're not. Yes. They're not stuck in the gravity field of the stars of the Milky Way.
Yeah, if they come that close kind of to the center of galaxy, they pretty much are kind of dissolved, and kind of all of the stars are getting separated from, they're no longer kind of in this tight galaxy that kind of.
Do the small ones have black holes as well?
We think they do, but that's a very active area of research. We kind of really, another test of dark matter is kind of how it's distributed in those small galaxies, and it's, yeah, the central question is whether it's very dense at the center, or whether it's kind of more flat density in the center. And that's why people really want to know if there are black holes inside them as well, because they're also dark, and we kind of don't see them, and they're very massive. But yeah, I think the idea is that they would have a black hole. It's just a question of how massive it is at the center.
And if the small galaxies, so is this what you call baby galaxies?
Or we call them satellite galaxies. It's just because they're actually fairly old. So yeah, it's kind of they stopped growing. Basically, when the galaxy enters a bigger galaxy and becomes a satellite, it kind of stops its own growth. It's no longer kind of forming new stars, because most of the gas is taken by the big galaxy.
Oh, so it doesn't have, because when stars are born, they are born in these huge gas clouds together.
Yeah.
And that's why they are born as clusters.
Yes.
You don't.
There's kind of a giant cloud of gas that kind of fractures, and like each kind of fractured splinter forms one star. But yeah, you do need a lot of gas, and yeah, it's a very inefficient. I guess depending on how you look at it, it's a somewhat inefficient process. You need, I think, 3 times as much gas, at least, as the mass of the stars you want to form.
So you see room for improvement here.
Well, yeah, nothing really we can affect on our own, but other than just kind of
Very
observe
long
it.
term. Yeah. Is it the crab? What's it called? Crab nebula.
Mhm.
That's one of those things where the krabbetokken in Norwegian. The crab nebula. That's one of the nebula where the stars are born, right?
I think actually that's the one associated with a supernova at the end of a life of a star. Let me just
Okay,
quickly
it
double
was
check
born.
this.
I'm just saying something wrong here.
Oh yeah, so this is yeah, kind of what's left after an explosion of star.
Oh, the Crab Nebula is after an explosion. The Horsehead
Yeah.
Nebula, that's where they're born.
Yes, the Horsehead Nebula is where they're born. Yeah.
Okay.
Yeah. So you can kind of see that there's kind of like those dark clouds, and because of the gas is in some parts very dense because it is forming stars, and then illuminated from kind of behind by the newly born stars. Yeah.
From behind or from inside?
Yeah, from inside, I guess. Yes. From inside of the cloud, like it kind of in projection, it's kind of behind the dark cloud for us. Yeah.
The Horsehead Nebula looks pretty awesome, and it deserves to look pretty awesome. So these tiny galaxies, the 60 small ones, how small is small in galaxy?
Yeah, that's I mean, like
I
you
feel like-
probably heard for the biggest one. That's the large Magellanic Cloud.
Oh, the Magellanic Cloud is one of the satellite galaxies.
It's one of the satellites. Yeah, it's the most massive satellite, and we think it just kind of came in. It just joined our galaxy. I mean, and by just, it's kind of maybe a billion years, but it's kind of the most recent acquisition. Let's say. So yeah, that's the biggest one, and then some of the smallest one maybe only have like 1,000 stars or so. They're like very small, and they're really hard to tell apart from just the regular star clusters that don't have dark matter. So it's really kind of blurring this distinction between what a galaxy is and what a star cluster is.
So yeah, because it's if it has less stars than it should compared to its mass, then you can safely call it a galaxy, because then it has dark matter. So and this is also one of the possible bullets.
Yeah, in principle, yeah. It's just that we expect there should be thousands of small clumps of dark matter, and there are only kind of 60 of those satellite galaxies. But so we think that kind of in just terms of number, it's maybe less likely that they hit like our stream of stars. But on the other hand, we at least know where they are, so we can kind of trace them back and see if they actually did hit it.
And did you try that?
I did try that, at least for the ones that we have measured orbits for, and yeah, we didn't see that any of them comes close enough to do that sort of hole. But yeah, we probably need to check this in some more detail, because we did assume kind of when we are tracing back the orbits of all of those galaxies, we assume something about what those orbits are. And so maybe there is some room for this impact still for the bullet to have been one of those satellites that we haven't tested yet.
So the chance of it being star clusters or galaxies seems small, because there are too few star clusters roaming around to statistically be. It's statistically unrealistic that one of them would happen to strike one of the other star clusters, because there's too few of them, really.
Yeah, it looks like that's kind of one way of looking at it, that there are too few of them, and then it would be very unusual if it was one of them that hit it. But it could be that this was something unusual. So
yeah.
Yeah.
You've only seen this once. I thought you'd seen traces more than once in many places.
Yeah, we have seen like some indications in other stellar streams that there are some holes in them, but yeah, this was kind of the cleanest one, and one that is in a stream that is kind of close to us. I mean, that's kind of in astronomical terms. It's still 30,000 light years away. So yeah, not very close, but close enough that we can see many stars, because in streams that are farther away, stars are kind of too faint, so it's kind of more difficult to observe them. But in some of those more distant streams, we also see evidence of such gaps. But we didn't, look into them in as much detail yet.
So what you're thinking is there are a huge amount of invisible, gigantic bullets that we cannot see before it's too late, floating around, ready to hit anything.
Yeah, that's our preferred cosmological model. It's not just me. It's kind of what we think this is our best guess of what the universe is.
Are they moving? How big are they?
Oh, they're kind of big. Kind of a typical size is maybe 300 light years. If they're well, it depends a little bit on mass. So the more massive are bigger. But if they have a mass of 1 million solar masses, which is kind of what we require here in our case, so they're like not too small, but still kind of much smaller than anything we've seen so far. Then they would have a size of 300 parsecs or 100 parsecs, which would be 300 light years kind of in size. So they are predicted to be somewhat low density.
Very big.
Yeah, they're kind of big. It's not like a black hole. So maybe that's where kind of the bullet analogy is not the most appropriate, because the bullet is kind of something that is kind of very dense, and we think that at least in kind of the standard theory, we expect those to not be super dense. They're not like black holes. They kind of have much lower density, which is like slightly interesting, because what we are finding for this stream, that we actually do require something that has a higher density. So in that case, actually the bullet hole is maybe more appropriate. So it might be that we are finding something new, learning something new about the kind of what those clumps of dark matter look like. Maybe they are more compact than we initially expected, or maybe it's not dark matter at all.
The one finding you actually made is deviating from what you were planning to find. The one bullet hole.
Yes.
The one actual bullet hole you know about doesn't follow the theory of what you were planning. Okay.
Yeah, so, to some extent, we were surprised. We did expect the kind of the.
So you were expecting to find something like this. You were, even before you found it, you were expecting to find traces of 100 light year and 1 million solar mass balls.
Yeah, I mean, like maybe expecting is not the right word, but that was a prediction in my field, astronomers who studied this even before I entered college or anything, they suggested that those holes should be there, because there are so many or predicted that to be so many of those small clumps of dark matter that eventually they hit a stream and leave that hole, so that now that we should see some of it. But of course, for a long time we didn't have good enough ways to isolate the stars in those streams. They're kind of just blended together with other stars in the Milky Way, so we couldn't like see if there are any holes at all. And now if well, I guess first we didn't know if you'll be able to do it, and even if you are, you kind of, there are always some odds. So there were expectations that for this particular stream of stars, it should have been hit by something, but like kind of one or two things in the past 10 billion years or so. But you know, it could be one or two or zero. So it's like you never quite know until you go and check. So we were kind of not surprised to find something. It was definitely not a guarantee that we will.
You were the one who found this.
Yes, I was working with a close friend and collaborator, Adrian Price-Whelan, a couple of years ago, and we found this together.
Who?
Adrian Price-Whelan.
Okay. And this must have been quite big.
Yeah, I think it was. It was a very exciting time, and it kind of came as a part of this data welcoming party or so. I'm not really even sure how to call it. So it was, yeah, it's a little bit nerdy, I admit. But there's this European space mission called Gaia, and it is kind of it's kind of far away from the Earth. And what it does is just continually imaging the sky and measuring positions of stars very, very precisely. And it just like, once it finished, like does a one round or across the kind of whole sky, then it starts doing that again. And it's measuring positions of stars very precisely, such that when it sees the same star a few times, it can kind of see how much it moved. And you know, when you go out and observe the star and you go out the next year, all of the stars look kind of there at the same place. That's because the stars are moving very slowly, or they're very far away. So we observe, like we don't really see them moving. But this mission is measuring this these positions very, very precisely, such that it actually can detect motions of stars. And that's mission. It has been kind of 20 years in the making, and the kind of planning stages, and then the launch, and then collecting the data for a few years. And like huge teams of scientists all across Europe have been analyzing those data. And what was it? I think April 25th of 2018, they released all of that data, all of the motions of stars, openly to anyone in the world. And so many astronomers were kind of planning for that day, because it was really the first time that we knew kind of how fast and where the stars are moving. And it's not just like a few stars, it was for almost 2 billion stars we have such measurements. And so it was just kind of a giant change in kind of how we do astronomy. And I was a part of this group of people at the Flatiron Institute in New York, who were just wanted to kind of hang out together and play with the data a little bit and see what's in there. And Adrian and I decided to look at this GD1 stellar stream. It's the name. And then, yeah, we found like those holes, and we're like, what's that? So yeah, it was kind of exciting on its own, but also exciting because it was part of this huge new thing that was coming together, and we were kind of part of that event. I think it was just a lot of fun.
How quickly did you strike gold from you got the data till you found it?
Oh yeah, that was like super quick. And just kind of like a lot of the credit goes to the team who analyzed the data and we created like this nice catalog. We really got it like in 2 days, basically. We got Yeah, and part of it is just um, kind of learning how to read the data at all,
Ah,
and then we're like, oh, we've started with like a small part of the stream,
mhm.
small part of the sky, and they're like, oh, it looks like it's continuing, and then we're like, okay, let's create a bigger box, and it's like, oh, it still don't have the whole stream, let's go bigger, and kind of there's like
Mhm.
kind of a little bit of testing, but yeah, everything came together so quickly, and we I think by day three we kind of had our basic result ready, and then in a week we wrote the scientific paper and submitted it to the Astrophysical Journal. Um, so which yeah, and that usually never happens. It kind of takes months to a year like for that process, and there excuse me, it was just yeah, everything happened in the span of a week.
Has this become, and then the tabloid news picked it up very quickly as well, and then I got to hear about it.
I think that came up a little bit later, because in this first, like in the discovery paper, we didn't say what it was, or like we
Mm.
just like say, oh, look at this, it's like it looks different than what we expect, if
Mm.
there's like nothing happening to the stream. But then actually my kind of numerical experiment where I simulated the stellar stream and something hitting it, that took a while to develop, and like to get the exact kind of orientation of the relative orbits of the stream and the bullet to produce what we see in the sky. So that kind of took, yeah, I would say 6 months, which is more similar to to a usual scientific timescale. And then yeah, I guess that was picked up after I presented that work at a scientific conference. Yeah, so I think that anyway.
Has this become your main focus in work now? Because of the
Yeah,
talk? Yeah.
pretty much. I try to diversify a little bit and kind of take a step back. But yeah, I think it's still a very exciting prospect, and something we need to follow. And actually, in a few weeks, on December 3rd, there is a new data release coming from this mission, Gaia, and it's it's not going to be quite the same revolution as it was before, because before we had no motions for 2 billion stars. Now we'll have a factor of 2 better motions for 2 billion stars. So it'll be still, I think, very useful for many of those streams, because they most of the stars in them are faint, and so this new data will provide more precise motions, and so I think we'll hopefully see something interesting in some of those more distant streams as well.
So the actual bullets, they could be star clusters, but there's too few of them, so that would be very, very strange. They could be dark matter, but the one we've seen, the one you've seen, you and Adrian have seen, indicates a smaller object. I think it was between 50, 60 light years.
Yeah.
Yeah. And also much more massive than, or it's still 1 million solar masses, but more.
Yeah, for that mass, it's more it's smaller than we would expect. So it kind of has the expected mass, or rather, it's again hierarchical. There are many more of the small ones, but yeah, it has like this. It's in the range of mass that we expected. It's just much smaller than what we would expect for that.
The diameter is smaller, but the mass is. So dark matter might be more massive than has been proposed so far. So you and Adrian might have been the first people to discover that dark matter is more massive, and that could have effects like the dark matter halo around the galaxy is smaller than we suppose, maybe. Yeah,
that's a good question. If actually that scales to the Milky Way as well, it really kind of has to do with what the kind of how the matter is distributed. And in the yes, what we're finding is that it's denser, like and those small clumps, that it's denser than what we would expect in standard theory. And of course, yeah, there is also a very big question of kind of how dense is the Milky Way's halo, and kind of to know that we need to measure precisely the distribution of dark matter in the center of the galaxy. And as you can imagine, it's very hard because we don't see it very well. It's kind of enshrouded in dust and kind of other stars. So yeah, it's we would definitely be like, if this turns out to be dark matter that's kind of denser, it would change our expectations of what we for the Milky Way's halo, but it might not be that it also is denser the same way, because there are some differences in kind of how kind of the mass profiles of small clumps versus big clumps like big halos like the Milky Way's.
When you say halo, if it's made of clumps, then the halo isn't made of like a foggy mass. It's more like the halo consists of clumps relatively evenly distributed in a certain spherical shape-ish. Is that correct?
It actually has both. So there is this kind of smooth component that as you say, is kind of foggy, and then it has a many of those small clumps. And
we think we don't know anything.
Yes.
Yeah.
Yes. Exactly. Yes. we just see that there is something, but yeah, we
both see indications that there is a foggy dark matter, and indications. You see indications. You're the only one who's found the indications of the lumpy dark matter, isn't it? Has anyone else
If it is
seen
dark matter, yes. There are some other observations of external galaxies. I don't know if you had a chance to come across those gravitational lenses.
I don't know. Yeah.
No.
Tell me.
Yeah. It kind of looks like the bottom of the wine glass. It kind of you see through that. It's kind of very distorted. Some galaxies look like that when we observe them on the sky.
Oh, really?
Yeah, and that's because they're kind of just behind like some other another galaxy or a cluster of galaxies, kind of along our line of sight. And this, they look very funky. But the thing is, because we kind of that kind of the bending of the light is caused by this galaxy in between, and in a way, then, like, from the shape of that galaxy that is lensed in the background, you kind of may be able to tell kind of how the mass is distributed in that galaxy in the front. And anyway, to kind of cut the long story short, there is some evidence for kind of, they are called lensing anomalies. So looks like this, you can reproduce some of those lensed galaxies if you include a small clump in that intervening galaxy. But those are kind of massive. They're of the size of dwarf galaxies that we see, or satellite galaxies that we see in the Milky Way. So they're kind of 100 million solar masses, not a million solar masses.
So you mean that we can see some galaxies far away are being distorted by gravitational lensing, like in the bottom of a wine glass, but there's no galaxy in front of them to do the lensing?
Oh no, there is the galaxy in front.
Okay.
Yes. It's just that galaxy in front has its own dark matter.
Yeah.
And to kind of to get that weird shape that is distorted, you need to know what the exact distribution of dark matter is in that galaxy. And so most of the effect is just explained by kind of a spherical halo of that is kind of smooth, hazy blob of dark matter.
Mhm.
But like some details require there to be a clump of dark matter as well.
Okay.
Those, or like in a few of those. Yeah. So that's kind of a different way of looking for those low mass clumps. It's just that, I guess, the precision that we have now in measuring those features is only so good. And so with that method, we can detect clumps of dark matter that are kind of 100 million solar masses rather than a million solar masses.
So, and the third possible explanation for the bullets would be supermassive black holes moving around.
Yeah. As we were saying, we are finding that this is a very dense object, and supermassive black holes have basically infinite density, or because they're very small. That would be very weird. I think that would be even weirder than a star cluster, because we kind of know of one black hole in the like supermassive black hole in the Milky Way, and it sits in the center. It's not like in the it's so far away.
So it would be a supermassive black hole that has escaped from the core of another galaxy and just swooshed through ours. So it would have been thrown through the universe by maybe another even bigger black hole to shake it out of its position, and then that's the only thing that's good.
Yeah, no, that's exactly what I learned, because when I first thought about it, or when I first saw our results, and it was like, okay, I guess it could be a black hole, but I don't know what it would be doing. And then I learned that the people who are simulating the arrival of those small galaxies into the Milky Way, they say that some of those galaxies kind of lose their black holes along the way, or kind of they are deposited in the Milky Way on their own, and take some time to kind of get to the center. So for a while they are kind of orbiting in this outer parts of the Milky Way.
You mean from the small ones, the satellites?
Mm-hmm.
Okay,
yeah,
but they don't.
Ones.
But they wouldn't have black holes on that scale, would they?
Yeah, they would be less massive, I think. So then, we need to kind of test a little bit, kind of how low mass can our bullet be, if that is still consistent. Okay. But I was shocked at all that there is a way to have somewhat massive black holes in the kind of outside of the center of the galaxy, and it's really coming from those small ones, as you say. They're kind of from a different galaxy ejected away.
Yeah, if I understand right, the only way to have a black hole would be to have a Milky Way-sized galaxy somewhere else, and then have it meet a much bigger galaxy and get destroyed and lose the black hole. Is that crazy?
Yeah, that doesn't quite work in terms of mass, right? Because if there is a galaxy more massive than the Milky Way, then probably we would be the satellite. Like we as the Milky Way would be the satellite. It's always like the most massive thing is kind of the main galaxy, and everything else is kind of a satellite. And we think that the Milky Way, at least in its own neighborhood, is kind of its own thing. It's not a satellite of something else.
Okay, but the Milky Way is part of a supercluster of galaxies as well.
Yeah, but it's in a kind of very far away.
The cluster. Yeah. Oh, the cluster is very loose and very.
Yeah, we're kind of not at the center of it, or anywhere close to it. Yeah. So in those terms, Milky Way is kind of considered to be just kind of out there on its own, and having the Andromeda Galaxy as a kind of companion, but not a very close one. So they're all kind of neighbors, but well separated from each other.
Mm-hmm. But all these galaxies are moving in a similar direction?
Well, let's see. I guess the Milky Way and Andromeda are kind of getting closer
Mm.
together, and yeah, it turns out that I think in a few billion years they will actually collide
Mm.
and form one galaxy. They are kind of moving towards each other. They're not like I guess yeah, but maybe in a relative sense that they might be kind of part of a group that's kind of moving somewhere together, but kind of locally looking at it,
Yeah.
yeah, it's
There's something called, I learned about the great attractor while swimming in a swimming pool with a very big man. So it was very memorable. He kept, his tiny daughter was swimming around him, and he's 2 meter tall, and told me about the great attractor, and it was very visual.
yeah, that's I mean, in principle, like the faraway galaxies, yeah, they kind of all look to be moving away from us. But kind of when you look at it on a kind of small scale, then it's a little bit different. So that's why I was hesitant to say, because I'm not exactly sure if like all of the nearby galaxies are moving in the exact same
Yeah.
direction. Yeah, astronomers like to call this that the kind of nearby galaxies have peculiar velocities. So there's kind of this main direction of motion, but they also have this kind of peculiar component that maybe actually, you know, it's deviating from that main direction. And I'm not exactly sure kind of where like the nearby galaxies are moving to, except for Andromeda. I know that Milky Way and Andromeda are kind of getting closer. Yeah.
Oh, and then there's the expansion of the universe on top of this. So,
Yeah.
of course, I was calling you because I'm also making a science fiction story, comic or something,
Wow.
with where the story is it's 300 years in the future, and the main
Okay.
characters are children. They're astronauts trained to go to work when they're 10 years old. And the
Whoa.
reason we're sending astronauts into space is we need someone to work their whole lives in spaceships, because we need to get away because there's a cosmic bullet coming our way.
Ah.
So I was thinking about giving a sci-fi threat that felt as existential and terrifying as climate change, and making it about something else, so we didn't have to sit and read about climate change all the time. And so yours
Yeah.
fit the bill.
I hope it's not it doesn't end up being that disruptive to our civilization.
So if such a cosmic bullet was coming this way, would we notice anything, or would it just go through us like a wave of water? Would just change the sun's position a little bit, and we wouldn't
Yeah,
notice it?
I think it depends a little bit on kind of how dense it is, but if
Mm.
it's just kind of a like regular density, yeah, we wouldn't really feel it.
Mm.
Like there are dark matter particles that are like passing through us all the time, or we are moving through the sea of dark matter with the sun, and it's partly because it's well because it's dark and in kind of physics terms, it's dark because it doesn't interact with ordinary matter.
Mm.
Um, and and yeah, people are actually trying very, very hard to detect any interaction of dark matter with like ordinary matter to kind of understand what it's made of. But so far, like we have detected nothing. So yeah, really kind of the thing maybe that might be kind of how we detect them is just through gravity. And so if they kind of pass by something and mess up like an orbit of an object or so, that we might be able to see that. But as I said, it's like we are looking for them in those streams, because otherwise it's kind of very hard to see the impact on kind of individual stars in the kind of like the sun as they're going through the galaxy. Um, Yeah.
You would notice that you would only notice that the sun has changed direction after millions of years because of the movement.
Yeah.
It wouldn't be immediately. It wouldn't be like, and the planets would still be in orbit around the sun just like normal, because the sun is much more massive than the fog of dark matter. So when you talk about
sun is not more massive than that hog. It's just that like sun like is stays around, and that would just kind of move past us. So it would kind of go by very fast and wouldn't have really time to mess up our solar system.
Oh, because gravitational influence needs time to influence.
Yeah.
Aha. It works through. Do neutrinos do the same? They move through us and we don't notice it.
Yeah.
Are they in any way related to dark matter, or is it a way to say the neutrinos are?
Yeah, we don't think they are. They like, so neutrinos were a good candidate for dark matter, just for this reason. Like,
let's just say what they are first.
Yes. Oh yeah. So they're like, well, to the extent I can. So they're very low mass particles that as you say, don't really interact very much with other particles in the that we know, like that make our body, like protons and electrons, and then other atoms and molecules. And yeah, they are very low mass, just kind of a fraction of a mass of an electron, and they move very fast. So, and because they move very fast, it turns out they can't, it's hard to kind of keep them all together. And we know that the dark matter, because it forms those massive halos, needs to be kind of stick around, and neutrinos would just kind of fly away, basically. So our best guess for what dark matter is that it's like a very massive particle, but some new particle that we haven't yet discovered. But in this standard model, the particle is kind of much more massive than the mass of a proton.
In which model?
Oh, it's I guess the standard model of cosmology. It's called cold dark matter, or lambda cold dark matter. Lambda being the kind of dark energy term that means that the universe is expanding, and cold dark matter being this model where the dark matter particle is very massive and then therefore moves kind of slowly, unlike neutrinos, which would make up a hot dark matter, but that has been ruled out because,
hot dark matter because it moves.
Yeah, it moves very fast because it's very light.
So you would call something hot if it moves a lot, and you call it cold if it stays still.
Yeah,
more or less.
Yeah, that's basically kind of how, but if you think of the air temperature, like if it's very hot, the molecules in air are moving very fast because just they have a higher kind of energy to move around, and kind of that's why we label those dark matter theories as hot and cold.
Okay.
Cold being because it doesn't move very fast, and it doesn't move very fast because it's massive. So rather than call it kind of massive and low mass dark matter, we call them cold and hot.
So the neutrinos move at light speed, right? Or
almost light speed. Yeah.
Almost light speed, but they cannot move completely at light speed because they are particles.
They have some mass. Yeah.
They have some mass. And photons, which is light, has no mass.
Yeah.
Photons are just what are
pure
photons?
Energy. Yeah.
But so photons are smaller than neutrinos, or we can't say small about.
Yeah, we can say smaller because I guess it doesn't really, or I don't think it has a concept of size if it has no mass.
They just hang around. And a weird thing that I just recently learned is that you cannot have anti-light.
Oh, yeah. That's...
As a cartoonist, I would love to have something called anti-lights. Just I'm using anti-lights, but you can't. There's the photons are their own
They're just
antiparticles.
photons. Yeah.
Yeah, they don't have a spin, so they can, because antimatter is electrons spinning the other way, and photons just don't.
Yeah.
This is as far as I got. Can you get me any further?
No, I'm sorry. It is a good concept, yeah, for sci-fi, I think. I guess it would be fantasy at that point.
That's that's always some good stuff to pick up there. So basically, Earth is safe from cosmic bullets unless they are made of black holes slung across the universe like gigantic, brutal ping pong balls.
Yeah. I think that's fair to say. And there are, okay, I don't want to be alarmist here, so you know, because I did get emails from people when that articles came out, or like, oh, is the end near? What's happening with this cosmic bullets? I was like, oh no, it's like, yeah, it's not dangerous for the Earth.
Very sorry, but my story will sell it as very unpleasant. They just go.
Oh, that's fine. That's not. It's not science reporting like you.
They just look into the sky, and then something's hiding all the stars, and they go, "Oh no!" And we don't even know. You don't even know how fast this thing would be moving. It's hard to calculate the speed.
Yeah. That turns out to be like the parameter that we had least constraint on, kind of how fast it was moving. And it's a little bit kind of goes in the opposite direction of mass, and kind of has this idea of that you need some kind of impulse to feel the gravitational effect. And you can have either a massive body that is moving very fast, or you can have a low mass body that is moving slow, and they would basically kind of have the same impact on the surrounding stars. And yeah, just because of the wide range in mass that is allowed, we don't really have a good sense of how fast it's going. So yeah, we saw that like if it's moving at typical velocities in the Milky Way, that it kind of works. So it's like, okay, that kind of makes sense. But yeah, we can't really precisely say exactly that's the velocity. But just to say, like the typical velocities in the Milky Way are something like 200 kilometers per second. So maybe I should like I guess multiply by 3,600 to get kilometers per hour. Can do that.
Basically, even slow stuff in the galaxy is moving very, very fast.
Yeah, exactly.
So how is that the same with the cold dark matter, that the slow dark matter would also be moving very, very fast, just not so close to light speed?
Yeah, it's I guess yeah, I think they are related. Here I'm mostly talking about the kind of objects in the Milky Way, kind of separate stars and separate clumps of dark matter. Whereas in terms of this cold and hot, I was thinking kind of more inside of a given clump, how fast stuff is moving. But yeah, I think they actually are related as well. I don't have a number to give you of kind of how fast stuff is moving inside the clump. Yeah.
Oh, right.
So but definitely, much slower than the speed of light. Yeah.
Yeah, they would need to be quite calm to stay clumpy.
Yeah. Yes.
They wouldn't be able to stay a clump if they were too juicy, because then they must. Yeah. And that also changes when you change the size, and you change then. A lot of different things that would influence each other. Thank you so much for your time. Is there anything we haven't gone through yet? hope you want to read my comic. It's
Oh
this
yeah, for
this
sure.
podcast
When
is
it's due
sponsored
out.
by Cosmic Bullet, my sci-fi comic. It's on my. Currently I do science explaining for antibiotics and stem cell people, so I haven't worked so much with my personal projects during this weird little year. It's a good time to do as many money jobs as you can if you get them. So, but I work with that on the spare time. But yeah, it's basically I'll cut this out, but in the story, it is actually a Dyson sphere from another galaxy that they took they used dark matter to encode data from another universe, and then I crunched all the mass in the universe, and since the dark matter isn't influenced by the big crunch, the dark matter would stay the same, right? So when the universe was reborn in a Big Bang, the data from the former universe was still there in the dark matter.
Oh, wow.
Does that make some sort of sense?
Yeah, I mean, I could see it as a. I mean, I don't know like how it would work in terms of physics, but I could imagine this like people figuring out some way to encode that information
in dark matter, because that's the only way to survive the death of the universe, is to save it in dark matter, because that's the only thing that would survive a big crunch, right?
I mean, yeah, I'm pretty sure like you can go along with it. Yeah, I don't think anyone can like say like, oh no, this is not how big crunch works. Yeah, so I think that
so that's why they are sort of as soon as a few atoms start collecting in the new universe, they create like a life form, and the life form creates a more advanced life form, and it takes a bunch of planets around a black hole and turns all the planets into it's a super planet system. It's 50,000 planets around a massive black hole, and then it transforms all the planets to a huge Dyson sphere that uses the gravitation, the Penrose effect, and just slings stuff into the black hole and makes energy from that. So it uses the black hole as it's a massive engine. So it's like a ping pong ball with a tiny singularity in the middle, and then it opens a little hatch at the back, and then it scoots around the universe like one of those boats with soap in the end, you know.
I love it. It's a good concept.
I think I haven't seen it used. I just smushed it together from different things, and then it moves. And the reason they left their old universe is there was a parasite in it. It was like this disgusting little parasite thing, and they crunched their entire universe just to get rid of this maggot, this worm. It's like the worm in the apple thing is really the biblical snake is just them sending us a message. And so, of course, the humans have found these things again on Europa, under the ice on Europa.
Oh, they're so small. Okay.
Yeah, there's just these little things, and they seem very innocent and nice, and we've become friends with them and everything. And so the cosmic bullet to crush our solar system is really just come to crush Europa, and Earth was just collateral damage. So I think that's the plot so far. Of course, this isn't explained ever. It's just a lot of stuff happening.
Obviously, yeah.
So that's
it's a cool concept. And how long is the comic, or
that's why
it sounds like there's quite a story there, and like I'm guessing there'll be a lot of action too, so it might take a while to explain it.
I'm not sure if you'll ever see this, but I made 11 books before. I know how to make comics, but that's still I know this is gonna be this is just have to be, but it was all I had some different concepts, but the cosmic bullets was like, oh yeah, I want to do, that's the most terrifying thing I've ever heard.
Oh,
that'll happen. So you're a very big you were a very, very big inspiration, and it was very strange to meet you now, because this has been in my head for a long, long time. And then
Well, I'm so happy to hear that you were able to take something from, I don't know, I guess our mundane research life and make it into an exciting sci-fi story. I think that's so awesome. It's
oh, cool, thank you.
yeah, I've
I,
never thought like that that would happen to my research, but I was like, I love it.
Great. I will definitely share stuff with you when it comes along, if you want to, if you're a comics person
please
or
do.
a fiction person.
More a fiction person, but yeah.
What kind?
Or yeah, just kind of read fantasy, like yeah, I've been reading anyway. What felt like a good kind of never-ending source of like new books, the Wheel of Time. I started reading that during the pandemic, but then I kind of got like halfway through. I was like, okay, I need a little bit of a break. But yeah.
Yeah, right. I've been. I was very obsessed with the Xixin Yu, the Chinese trilogy.
Yes, I saw that. I only read the first book, and then when we agreed, and I was like, oh, it could be so fun, like to read the second book that you mentioned, but yeah, I didn't get
the second has the cliffhanger. It has a Mexican standoff of enormous proportions. You know the Mexican standoff, and everyone's got a gun to each other's head.
Mm-hmm.
He's got that, but the biggest the biggest standoff imaginable is just crazy huge. It's,
yeah. Okay. Well, but I think the third book is out as well. So, or no?
Oh yeah, it's all out. I heard him on audio. And I didn't know any of the names. It was just Chinese person. And then latched onto the ideas and enjoyed that. No, I think I have all I need. This last part was just me personally chatting.
Sounds good.
Mm-hmm.
So how often do you do you post podcasts?
I've got 5 now with you. Last one was Cynthia Phillips from NASA Europa. I'm just
interesting.
She's leading Europa Clipper, not leading, but she's the press person for Europa Clipper. And she's also amazing to talk to. She's just very good at explaining these things. I don't know how many people listen to like a Norwegian guy talking to space people, but I'm just collecting the best possible collection I can, and then it's there. It's gonna be there. And Robin Hansen.
I don't know the name. But I will say we said Cynthia Phillips.
I'll just link you to the whole thing.
Okay, please do. Yeah. I'm on our seminar organizing committee, and we always, need good people to give research updates as well. So we're always like on the lookout for new names, and if it's in fields that I don't know, then it's especially welcome, to know that someone is a good speaker and can explain well what they do.
About what? I'd love to collaborate with you guys on that. There was Robin is he wrote a book called The Age of M about mind uploads. What would happen if we could mind upload personalities to computers?
I think like this. Okay. I think this is like a very popular theme now with like AI becoming so and just kind of becoming more at home.
So actually this whole pod is me and my friend Tom Norheim in NASA JPL. We planned to. I'm a cartoonist and I do some science cartoons. I'll send you the stem cell book. Did I send you that?
No, I don't think you did.
It's
I think I just like I googled you and saw that you had books, but I don't Yeah.
Mostly in Norwegian.
Yeah. Yes. Yes, that
Um,
was the hurdle.
yeah. So, but after the stem cell book, I've gotten to do a lot of science comics and science explaining, and got to work with a lot of very cool people. So that's something I can definitely, for me, do and still feel like it's part of my artistic, what I want to do anyway. So that's fine. So me and Tom were planning to do a festival in Los Angeles called Drawn to the Stars, where I take my cartoon friends and he takes his NASA friends, and we all just eat pizza and drink beer, and then maybe show something of the, mostly just eat pizza. So that
sounds fun.
That would be awesome to have you come to when we can meet people again at some time.
Yes, I would love to, and hopefully, like anyway, we'll see. Maybe in a year or so, it'll be okay.
You live in Harvard, right?
Yeah, I'm in Cambridge, Massachusetts. Yeah.
That's
so yeah, like people here have been very sort of cautious, and you know, yeah, it was never like a complete lockdown that you're not allowed to go out, but people are kind of just very careful and like always wear masks, and yeah, I think most people still work from home, and now even just the businesses again started closing by 10, and so anyway, it just looks like we're not quite out of the woods yet. So,
yeah. So, well.
Yeah.
So that's something that would be nice to do in the future. And yeah, if you need a cartoonist for something, then just send a message.
Will do. Yeah. So you're doing like the biology stuff that you're doing.
Yes. Yeah. My drawing style works well with cells. It's I'm not a technical. I don't like drawing straight lines. Basically, that's.
Fair enough.
I'm too much. Yeah, I'm too much of a perfectionist. If I can't get the straight lines absolutely perfect, it's like, and then I get angry. So that's why biology was really nice for me. But of course, I have done all kinds of things. Just yeah. Have you seen Kurzgesagt, the YouTube thing? In a nutshell, it's animated YouTube videos with the space science. It's quite amazing. It's I would love to do something approaching that, but that's massive quality. It's amazing stuff.
Yeah.
Yep.
Well, good luck with that. And if I ever, think anyway. I mean, it's kind of eye-opening that to even. No, that cartoonists would be welcome to to do some kind of science illustration. So yeah, if I have something, I will get in touch.
Yeah, awesome. I have enough, so I'm not doing this just to grab jobs. It's just.
Oh no, I didn't take it that way.
Okay, good.
Sounds like you have a lot on your plate, but it's good.
It's fantastic to get to talk to you and to Robin and Cynthia and Tom, and it's so fun to notice how energetic and enthusiastic and humble the best scientists in the world are, in a way.
Oh, thank you. I'm glad that that's the impression we leave. We do try to be careful and not to overstate what we do, but it's also I do feel very fortunate to be doing what I do, and because it's just a lot of fun, and and well, I see also talking to you as a part of the fun, and yay.
You were just 27 when you found this huge finding. That was early.
No, I wasn't. Wait, I think I was more like 31 or so.
Okay, then the internet.
I was born in 86.
Must have messed up. I don't know.
Yeah. No,
but it's still very early.
Yeah. So, I mean, Like it's not like in the turn of the century, it's where like all of the Fermi was 20 or so, and when he can,
Oh yeah.
yeah,
Hmm.
that it's I think it's maybe typical for these days, kind of after
Yeah.
there's
Hmm.
kind of the established track of going to college and then graduate school, and now I'm in this postdoc stage where I'm
Hmm.
graduated, but I'm not a professor yet, and so
Hmm.
I dedicate all of my time to research. And I think,
Hmm.
yeah, probably a lot of the kind of for most people personally, that's kind of when they are kind of the most productive because this is kind of the years where they don't have to take classes, they kind of know how to do research, and they don't
Hmm.
have to teach or like they don't have other obligations that professors usually do. So I think that's kind of
You're
it's
happy to
not
know.
unusual. Yeah, it's like I mean,
Hmm.
like when you take any given scientist, you can see that they did kind of a lot of their work when they were in this transition between being a student and becoming a professor.
Yeah, I see. So you're dreading to become a professor then?
Well, it's not quite like that because this job, the position that I'm in, it's there's no job security. Whereas professor, like in principle, like well, I guess after a tenure review, then you are kind of set for life. So there's like a lot to be said for that.
Mm.
But yeah, I think most people who do become faculty and professors, they're like, oh, those were the days when we were
Mm.
not professors. Those are like the best days. It's just like when you're in it, and it's like, and they don't know kind of what comes next is a little bit uncertain. But
I
I
can
don't know.
recommend having no job security. It's awesome. That's
Yeah, I feel like that
that's
would not work with my personality.
um, it's well, it was 1 month of panic when the pandemic struck, but now that
Only one?
yeah, actually only one because
Oh.
turns out that yes, the art world is struggling, but the medicine world is not struggling. And who's the guy who's friends with the medicine world? So
Ah, that's well played.
yeah. So
Ah, that's so awesome. And do you like completely freelance? Do you live somewhere like remote or
I live in Oslo.
oh, you live in Oslo?
Yeah.
Okay.
So now I've
So
been
good.
in Bergen teaching and also helping a PhD guy to do his stem cell PhD on cartilage in the jaw.
Okay.
So after being an art teacher for a week, I went and sat 2 days with a guy and just yelling at him and telling him his presentation was bad and I literally I was very strict and he was so thankful and I was just encouraged, so I became an even bigger asshole. It was just he wasn't a storyteller, so
Mhm.
and he told me after 5 hours that he never actually read fiction.
Oh no.
So that's why his sentences were all like they didn't have a beginning, middle, or end. They were just sentences with information, but
Oh,
it came out with no build-up
right.
of knowledge. So I'm cutting that away as well. It's rude to put it. But so that was like a fifth potential job that I could do to just help fictionalize non-fiction. So that was nice.
Yeah, definitely we need more of that, I think, and especially since, yeah, it feels like if you see someone in person, you can kind of stop them and ask them. But if you just kind of look at recording, then it's really like it makes such a big difference if it's kind of thought out in advance and if it kind of has the
Yeah,
kind of arc of the story in place.
yeah.
Even if the delivery is not the best, if you kind of see where the buildup is and kind of what the resolution is,
Mm.
it's something you can kind of can stick with you, I think. So,
Yeah,
but
and that
yeah, you're
was
doing good work.
yeah, that was fantastic because his actual science was amazing, but
Mhm.
I just needed to like fight with him to get out what he was actually doing, and that was super fun but very exhausting. Like,
Can
super
tell.
duper. Yeah. Oh well, sorry for that. Was just funny. So that's how it
I
works.
enjoyed, meeting, meeting you and getting to know you a little bit more.
Yeah, you've got to come and drink beer with us in Hollywood when we are going there at some time.
I'd love to. Yeah,
So-
whenever you do it, keep me
Oh,
posted.
cool. Then we have you, and then we have James Fallon, and then we have NASA. Oh, that's good. And if you think about, if you see people, now you met me, so if you
Mhm.
remember or know any people that you think, oh, this person needs to go on Øystein's show, send them over.
Okay,
And
I will
then
do it.
hopefully Wunderdog will grow organically and just have like, a bunch of awesome folks. Oh, I won't steal any more of your time. I assume
Sounds
you
good.
have.
Yeah, we can wrap it up here. Yeah, it's a beginning of the day or end the week as well. So yeah.
Good start. Well, thank you very much. You've got anything more you want to say to on record before I shut off?
Yeah, nothing comes to mind. I don't know if you usually do like a closing or kind of how you end the episodes.
I don't think we kind of stopped organically. So I think, well, thank you
if you want to thank. Yeah. Okay.
Yeah.
Go ahead.
Okay. So thank you for joining this show, Anna Bonaca, and to everyone listening, please go and support me on patreon.com/runde. That's also where I put my comics and stuff, a lot in Norwegian, but also sometimes in English. And thank you.
Thank you.
Okay. Okay. Goodbye.
Bye.